In the last video patungkol sa first law of thermodynamics for control mass, pinag-usapan natin ang energy equation for closed systems at kung paano ito gamitin sa pag-solve ng iba't ibang problems. In this video, pag-uusapan natin ang energy equation for closed systems para alamin ang iba't ibang governing equations ng tatlong thermodynamic cycles, which are the power cycles, refrigeration cycles, and heat pump cycles. By the end of this session, you should be able to define what a thermodynamic cycle is. Bukod dito, dapat ninyong madaman ang mga energy balance equations for the three basic thermodynamic cycles na binanggit natin kanina. Finally, malalaman nyo rin ang iba't ibang performance parameters ng bawat thermodynamic cycle at kung paano mag-solve ng word problems gamit ang mga ito. So what is a thermodynamic cycle? A thermodynamic cycle is a sequence of thermodynamic processes na kapag pinagsama-sama mo ay nagsisimula at nagtatapos sa parehong state. Ibig sabihin, the end and the beginning are the same. Isang halimbawa nito ay ang steam power plant kung saan ang tubig ay paikot-ikot lang sa iba't ibang bahagi nito. Nagbabago ang state at phase nito mula liquid to vapor or steam hanggang bumalik sa pagiging liquid. So now let's discuss the three basic thermodynamic cycles. Una na rito ay ang power cycles. Kapag sinabi nating power cycle, ang pangunahing layunin nito ay mag-produce ng useful power output in the form of electricity mula sa energy na nanggagaling sa mga combustion gases. So halimbawa sa ating steam turbine power plant, gusto nating i-convert ang chemical energy mula sa ating fuel bilang thermal energy sa ating working fluid at high temperature and pressure. So, in this case, ang ating working fluid ay water o kaya steam. So, after nating makamit ang high temperature at high pressure, ang gagawin natin ay padadaanin natin ito sa tinatawag nating turbine generator na siyang magko-convert ng energy to electricity. So, from chemical energy sa ating combustion gases, gagawin natin siyang mechanical energy sa ating turbine. And then finally, sa ating turbine generator, i-convert ito to electricity. So, makikita dito sa ating slide ang schematic diagram ng isang power cycle. When we have power cycles, meron tayong dalawang uri ng heat reservoir. Yung isa na may mas mataas na temperature, which we are going to call the high temperature reservoir. At yung isa naman ay yung may mas mababang temperature, which is, of course, the low temperature reservoir. So what happens here when we have power cycle is that heat is transferred from the high temperature reservoir to a low temperature reservoir. And as a consequence of this heat exchange, meron tayong positive work output. So kung ilalapat natin to sa ating example a while ago, yung steam turbine power plant, ang high temperature reservoir ay yung hot combustion gases. Samantalang yung low temperature reservoir naman ay yung ating mga atmosphere or lakes o kaya rivers na nagsisilbing tapunan ng waste heat ng power plant, of course upon satisfying environmental standards for emissions. So kung saan mo itinatapon yung iyong cooling water sa condenser ng iyong power plant, dun yung ating low temperature reservoir. And of course, dapat masasatisfy nito yung certain temperatures kasi sa ating rivers and lakes, of course, may living organisms tayo dyan. And kapag umabot ng mataas na temperature yung ating waste water, ay magiging harmful ito sa kanila. Okay? So meanwhile, yung ating work output dito sa ating schematic diagram ay yun yung napuproduce sa turbine ng ating power plant, typically in the form of electricity na. No? So, there is just one assumption na kailangan nating i-apply dito sa schematic diagram na ito. So, when we are analyzing the thermodynamic cycles such as the power cycle, the refrigeration cycle, and the heat pump cycle, kailangan nating i-assume na yung energies na in the form of heat and work ay positive in the direction of the accompanying arrows. Okay, so let us apply the energy equation for control mass. So, sabi natin before, the change in energy in the entire cycle is just equal to the magnitude of all the energies going into the system minus the magnitude of the energies going out of the system. So here we have delta E cycle is equal to E in minus E out, or basically energy in to the cycle minus energy out of the cycle. So, sinabi natin kanina na ang thermodynamic cycles ay isang series ng thermodynamic processes kung saan ang initial state ay equal lang sa final state. So, that means na yung change in energy in one cycle is basically equal to zero kasi nagsimula ka at nagtapos sa parehong state. So, the energy possessed by your cycle as it starts is the same as the energy it possesses as it finishes, and therefore the change in energy is just equal to zero. So this expression can be replaced with Qin, while this one can be expressed or replaced by the quantity of Q out plus W out. So let's do some algebra here and distribute the negative. And then finally, we isolate W out. Ngayon, meron na tayong expression for the network output ng isang power cycle. The performance parameter associated with the power cycle is called thermal efficiency. So, makakuha natin ito gamit ang sumusunod na equation. We have the work output divided by the heat input. Now, substituting the numerator with the equation that we derived a while ago, we have the following equation for efficiency. So, take note na ang unit ng work at heat ay joules in SI units, no? Pero may mga pagkakataon na mga energies na ito ay expressed in terms of unit time. So, naka-per unit time silang lahat. In such cases, work in itself becomes rate of work, and heat in itself becomes rate of heat transfer. So, both of which are in watts, kilowatts, horsepower, or BTU per hour. So, depende na lang kung ikaw ay gumagamit ng SI units or English units. So, sa mga pagkakataong ito, maaari nating i-express ang thermal efficiency using the following formula. And if you can notice, kamukha lang ito ng previous formula natin, only this time they are expressed as time rates. So, time derivative, merong dot dun sa taas, no? Ibig sabihin, differentiate sila with respect to time t. Sunod, meron tayong refrigeration cycles. So, sa refrigeration cycles, ang pinaka-goal o pinaka-layunin natin ay makapag-produce ng cooling effect gamit ang power input habang nagtatapon ng waste heat sa environment. Makikita natin sa ating schematic diagram na ang ating system ay nag-a-absorb ng heat mula sa ating low temperature reservoir at tumatanggap ng work from an external source habang nagtatapon tayo ng waste heat sa ating high temperature reservoir. Sa ating refrigerator sa bahay, ang work input or Win, at in this case, mas appropriate na sabihing power input, no? Ang power input ay manggagaling sa outlet ng ating kuryente. Samantalang ang low temperature reservoir naman ay kung saan hinihigop ang Qin. So, saan ba may heat absorption? Of course, mayroong heat absorption sa loob ng ating refrigerator kung saan natin pinapalamig yung ating mga pagkain. So, samantala, ang high temperature reservoir naman ay yung room or any environment for that matter kung saan matatagpuan natin ang refrigerator. So, now let us perform energy balance in our refrigerator. Again, kung i-apply natin ang energy equation for control mass, we have the change in energy in the entire cycle, and that will be equal to the magnitude of all the energies going into the system minus the magnitude of all the energies going out of the system. So again, meron tayong delta E cycle is equal to E in minus E out. Now again, just like our argument a while ago, since it is a cycle and the initial and final states are the same, then this expression here will be equal to 0. So all the energies that are going in are Win and Qin. So papalitan lang natin tong expression na ito ng Win plus Qin. Samantala, ang energy naman na lumalabas ay ang heat rejected Q out. Simplifying this equation and isolating Win, we have Win equals Qout minus Qin. Again, when solving for problems involving thermodynamic cycles, i-assume natin na itong mga Win, Qin, and Qout ay magnitudes na lang, no? So, they are positive in the direction of the arrow. So, when you plug it into this formula, make sure that they are all positive. And again, this only applies when we are solving thermodynamic cycles like power cycles, refrigeration cycles, and heat pump cycles. Ang performance parameter ng refrigerators ay tinatawag na coefficient of performance, which is denoted by the Greek letter beta. So, minsan, sinisulat lang ito as simply COP, coefficient of performance. Ito ay makukuha gamit ang ratio ng cooling effect Qin at ng work input Win. So, as a clue, para mas madali nating matandaan ang formula, no, kung medyo nalilito tayo, pwede nating isipin na ang nasa numerator palagi ay yung desired output, which in this case, the cooling effect. Kaya tayo gumagamit ng ref ay para magpalamig. So, therefore, we want the cooling effect, we want the heat absorbed. So, samantalang yung ating nasa denominator ay yung mga input or investments na ginagawa natin, which in this case ay yung work input sa ating compressor. So, substituting the equation that we obtained for Qn, we have the following. So, again, just like in our power cycles, kapag ang mga given energies ay naka-time rate form, papalitan lang natin ang mga variables ng mga derivative nila with respect to time. Which is why they're practically similar, pero meron lang dot dito sa taas to signify that they are differentiated with respect to time. Finally, we have the heat pump cycle. Kung mapapansin natin, ang schematic diagram ng heat pump cycle ay parehas lang dun sa schematic diagram ng ating refrigeration cycle. From this logic, masasabi natin na ang derived equation for the work input will be the same for both. So, meron tayong same formulas, same derivation as before. Ano naman ang kaibahan ng ating heat pump cycle sa ating refrigeration cycle? So, kung ang useful output natin sa refrigeration cycle ay ang cooling effect, sa heat pump naman ay ang ating heating effect, Qout. Therefore, ang heat pump coefficient of performance gamma is denoted by the ratio of Qout to Win, which can further be expressed as this equation. Sa ating final slide, makikita natin ang summary ng schematic diagrams, ng governing energy equations at ng performance parameters both in standard and in time rate forms. So let's solve this sample problem. For a refrigerator with the automatic defrost and a top-mounted freezer, the annual cost of electricity is $55. Letter A, evaluating electricity at 8 cents per kilowatt-hour, determine the refrigerator's annual electricity requirements in kilowatt-hour. And letter B, if the refrigerator's coefficient of performance is 3, determine the amount of energy removed from its refrigerated space annually in megajoules. So, isulat muna natin yung mga quantities na alam natin. Sabi dito, ang annual cost of electricity ay $55. So, let's define C annual as our annual cost, which is equal to $55. Also, the unit cost is said to be 8 cents per kilowatt-hour. So, that is $0.08 per kilowatt-hour. Sinabi din sa ating problem na ang coefficient of performance ay 3. So, sa letter A, ang pinapahanap sa atin ay ang amount of energy requirement in kilowatt-hours. So, we have E annual. Let's define E annual as our yearly energy consumption. And logically speaking, masasabi natin na yung total cost ng ating electricity per year ay equal lang siya sa unit cost ng electricity multiplied by the annual consumption. So that is C annual is equal to C unit multiplied by E annual. We can isolate E annual, and that gives us C annual divided by C unit. Substituting the values that we know, we have $55 per year divided by $0.08 per kilowatt hours. And as you can see, the dollars will cancel each other out. And yung kilowatt hours naman natin ay mapupunta sa numerator. If we plug it into our calculator, we have 55 divided by 0.08. That gives us an annual energy requirement of 687.5 kilowatt hours. Let me just write that down. And there you go. Now, for letter B, the one that we are looking for is actually the amount of energy removed from its refrigerated space. So, ibig sabihin, pinapahanap sa atin yung Q input. And in our schematic diagram over here, let's complete this first. Alam natin ang purpose ng ating refrigerator ay magbigay ng cooling effect sa pamamagitan ng pag-absorb ng heat mula sa isang low temperature reservoir. And because of this, it has to reject heat at a high temperature reservoir, and it has to absorb energy input from an external source. So, this is our Win. So, kung iisipin natin yung value ng E annual na sinolve natin kanina, that is just your energy consumption for the year, or basically the energy input in your refrigerator. So, we can say that Win is just equal to E annual, which is therefore equal to 687.5 kilowatt hours. Since we know our COP, or our coefficient of performance, and we know na ang coefficient of performance ay equal lang sa amount of cooling effect Qin divided by the energy input Win, we have this equation. Isolating Qin, we have beta multiplied by Win, and then we substitute the numbers that we know, beta being 3, and Win being 687.5 kilowatt hours. This gives us an energy absorbed that is equal to 2062.5 kilowatt hours. So let me just write that down. Are we done? If we go back to our problem, it says here that we are asked to solve for Qin essentially, but in megajoules. Sa ngayon, ang meron lang tayo ay Qin in terms of kilowatt hours. So the question is, how do we convert kilowatt hours to megajoules? So take note that kilowatts is just equal to kilojoules per second. Therefore, kilowatt hour is just equal to kilojoules per second multiplied by R. Therefore, we can write this quantity to 2062.5 kilojoules per second, R. Now, let's practice our dimensional analysis skills and recognize that for every 1 megajoule, there are 1,000 kilojoules. And for every R, there are 3,600 seconds. Substituting these values in our calculator, we have 2062 multiplied by 3,600 and then divided by 1,000. This gives us a final answer of 7,425 megajoules. So this is actually a lot of energy being taken in. And of course, understandable naman kasi isang buong taon yan. I hope you understood the first problem that we solved. If you have questions, you can just comment down below. For now, let's solve another sample problem. For the sample problem, we have a power cycle. A sports car engine delivers 100 horsepower to the drive shaft with a thermal efficiency of 25%. The fuel has heating value HV equals 40,000 kilojoules per kilogram. Find the mass flow rate of the fuel required in kilograms per second and the combined power rejected through the radiator and the exhaust. We have two hints over here. It says that the rate of heat of combustion is equal to the mass flow rate m dot multiplied by the heating value HV. Also, 1 horsepower is equivalent to 0.746 kilowatts. So, isulat muna natin yung mga given, mga alam nating values. We have W dot out, that is equal to 100 horsepower. So, take note that our system here is the engine, and the engine is undergoing power cycle inside it. And the output work, the one to be delivered to the drive shaft, is 100 horsepower. Therefore, W dot out is equal to 100 HP. Also, the thermal efficiency is equal to 25%, or in decimal form, you have 0.25. And finally, the heating value HV is equal to 40,000 kilojoules per kilogram. So by the way, kapag sinabi natin heating value, it is just the amount of energy being released by a fuel per unit mass as it undergoes combustion. So habang binaburn mo yung fuel, it will release an amount of energy. And if you have 1 kilogram of fuel, the amount of energy being released by that 1 kilogram of fuel is equal to your heating value. So what we are looking for are the mass flow rate m dot in kilograms per second and the power rejected q dot out at the radiator and the exhaust. So kahit walang binigay na unit dito, i-assume natin na ito ay naka-kilowatts. Now, since the mass flow rate of the fuel that we are looking for is in kilograms per second, it is in SI, therefore, we need to convert our 100 HP to SI unit. So, alam natin, according to our hint, na per 1 horsepower, we have 0.746 kilowatts. This further means that 100 horsepower is equal to 74.6 kilowatts. This is our W dot out. Let us complete our schematic diagram para alam natin yung mga nangyayari sa ating problem. Sa ating power cycle, ang pinaka-objective ay makapag-produce ng power output provided that we are absorbing heat from a high temperature reservoir, so we have Q dot in over here, and rejecting it to a low temperature reservoir. So we have Q dot out over here. So in this case, our W dot out, we have calculated it a while ago, we have converted it, and it is equal to 74.6 kilowatts. Sabi natin sa lecture natin kanina, ang ating high temperature reservoir ay ang ating combustion gases. Therefore, we can just say that Q dot in is just equal to the heat released during combustion. That means lahat ng rate of heat na nilalabas ng ating fuel through combustion ay inaabsorb ng ating engine. So we can say that Q dot in is just equal to Q dot combustion. So let's begin with what we know. Alam natin na ang thermal efficiency equal lang yan sa power output divided by the heat input or the rate of heat input. We know that the thermal efficiency is 0.25. The power output is 74.6. And Q dot in is the one that we're looking for so far. Isolating Q dot in, we have 74.6 kilowatts divided by 0.25. Let us now plug them in our calculator. We have 74.6 divided by 0.25. We have a rate of heat input that is equal to 298.4 kilowatts. Now, we are going to equate 298.4 kilowatts with the mass flow rate of the fuel, which is the one that we're looking for, multiplied by the heating value, which is 40,000 kilojoules per kilogram. We know that kilowatt is just kilojoules per second, so we can replace this unit. Finally, we have m dot. It is equal to 298.4 kilojoules per second divided by 40,000 kilojoules per kilogram. The kilojoules will cancel out, and the kilogram will be on the numerator. Therefore, the unit of our mass flow rate in this case is kilograms per second. Plugging these values into our calculator, we have 298.4 divided by 40,000. That is equal to 7.46 times 10 to the negative 3 kilograms per second. So let me just write that down. Now, this is our final answer for the first part of this problem. Moving on to the next part, pinapahanap sa atin ng Q dot out, which is the power rejected through the radiator and the exhaust. So it can be solved by conducting an energy balance in your engine. So that is all the energies that are going in, which in this case is just Q dot in. It's equal to all the energies that are going out. So we have Q dot out plus W dot out. Take note that Q dot in, we have already solved for it a while ago. That was equal to 298.4 kilowatts. And W dot out is equal to 74.6. So writing down those values, we have 298.4. It's equal to Q dot out plus 74.6. Which means that Q dot out is just equal to 298.4 minus 74.6. Plugging this into our calculator, we have 298.4 minus 74.6, which is equal to 223.8. So this is now our power rejected in all the heat sinks that we have. That's it for this video. I hope you learned something and tune in for the next videos.